Okay guys, first stream of the day. Let's kick it off. Let me just share the link on Discord as usually. Link. So today, a couple of things at our plate. I want to profile Apex because I managed to get it to work last night thanks to Aleksa's contribution. Let me show you that one. So we go here, open NLLB project. Here is a contribution from Alex. He basically added these instructions that you need to install CUDA deltkit and CUDA NVCC 11.3 to make this installation of Apex work. So that fixed it for me as well. So now we can now use fused kernels, which means the runs will be faster. I'm not sure how much faster, and I wanna profile the runs as a part of this stream. That's gonna be one of the things. And also we have two empty papers, classics that we need to read. So I'm thinking what's the best way to do this. I think we can maybe start while we're fresh with the papers actually. Let me see for a second how this is progressing. Let me open up Stopes. I kicked off a run here. So we are kind of halfway there when it comes to filtering the data, because last night unfortunately I stopped it and didn't run it, so it didn't finish, but it's gonna run in the background. And we also want to push to Flores 202, so we have to prepare Flores 202. Push it through the, I guess, yeah, we don't have to do anything there. We don't have to filter Flores 202 because it's already curated. So we just need to basically binarize it so that we can use it as the evaluation test during the run. And then we want to start playing with mine data as well in parallel. So that's kind of the task for this stream. I think we can start with the empty papers. So let me just tell to Rafael here. He asked whether I'm not sure. Rafael, are you on the stream? We are going through the papers. Okay, let's open up these two papers. Scaling neural machine translation. I'm fairly sure I haven't read this one. I read mostly papers related to NLLB, laser, stuff like that. Let me open up the second one. These are more of classics of MT. I guess it's now that we're trying to build a system, having more background in machine translation will definitely help. I was ill last week, but I will try to catch up with your videos. Hey, what's up? Hey, no worries. I think the best way to catch up is to just be present in the channel here on Discord, open NLLB. I'm doing a ton of stuff that not necessarily everyone has to go through on my videos. We want to parallelize this as much as possible, so don't worry too much about it. Okay. We can start with scaling neural machine translation. Let's basically let's go through these two while my Stopes filtering is running, and then we can profile Apex and prepare eval data. I think this is a reasonable prioritization for the stream today. And hopefully by the end of the day, we manage to get to the point where we can literally kick off a run with 650 million. I'm going to scope down the number of languages. Obviously, we currently only have, I think, around 94 languages because we're not using mine data. So out of those 94, I'm gonna probably scope it down even further to just some similar high resource languages we currently have supported. I'm gonna kick it off, and then I'm gonna use Flores 200 to track the progress on those particular language directions as well during the training, just to see whether we can get this to work. We will have to enable in the long term the four-stage curriculum learning as well, because otherwise we can't train that many languages using a dense checkpoint. It's going to be hard as it is with just using a dense checkpoint. So enough rambling. Let's start reading. Let me open up the paper. Scaling neural machine translation. FAIR and Google Brain, both organizations involved in translation a lot. Facebook internally, Google with Google Translate as a commercial offering. So let's kind of skim through the abstract first. Sequence-to-sequence learning models still require several days to reach state-of-the-art performance on large benchmark datasets using a single machine. This paper shows that reduced precision and large batch training can speed up training by nearly 5x on a single 8 GPU machine with careful tuning and implementation. Just see the link one. Okay, the implementation is available in FAIRSec. On WMT14 English-German translation, we matched the accuracy of the original transformer paper in under 5 hours when training on 8 GPUs, and we obtained a new state-of-the-art of 29.3 blue after training for 85 minutes on 128 GPUs. Nice. We further improved these results to 29.8 by training on the much larger Paracroll dataset. Hey Rafael, welcome man. We just started reading. On the WMT14 English-French task, we obtained a state-of-the-art blue of 43.2 in 8.5 hours on 128 GPUs. So it's all about scaling neural machine translation. They mentioned the original paper, and then they say in under 5 hours on 8 GPUs, 8.5 on 100. I'm trying to consolidate these two facts. They're training, they match the accuracy in under 5 hours on 8 GPUs, and we obtain a new state-of-the-art after training for 85 minutes on 128. Okay, so that makes sense. And then they mentioned reduced precision. We'll see what they mean by that. Is it just FP16? Because maybe back in the day that was not as common as today. Okay, let's kind of skim through the main charts first, and then we can go through the details. Validation loss for transformer model trained with varying batch sizes as a function of optimization steps left and epochs right. Training with large batches is less data efficient, but can be parallelized. Batch sizes given a number of target tokens, excluding padding. Okay. So let's see. The bigger the batch size, given the optimization steps, obviously we see more data, so the loss, validation loss goes down quicker, and then epochs. With the actual epochs, it's less efficient, as you can see, because now the 400K, the biggest batch size is slower when we look at epochs. Okay, let's skim through the results here. So re-implementation of the transformer, they achieve on-pair results, less updates, but more tokens per second. Okay, that's the reference, and then this is, I guess, the lower precision 16-bit. I wonder whether they used bfloat back then. I'm not sure when bfloat was. The brain float format was created that has higher dynamic range. I'm not sure what this is. We'll see what it is. 2x LR, 5K tokens per GPU. speed up. They're looking at speed ups here. So here with this one they get 4.9, and then 60 nodes they get to 44.7x speed up, 128 GPUs, much bigger batch size. Ampere blue, less updates because more tokens per batch size, I guess. Higher throughput, less time, as we can tell by the speed up. Training time in minutes for reduced precision. Accumulating gradients over multiple backwards. Okay, that's this parameter. Increasing learning rate and computing each forward backward with more data due to memory savings. Average time over 3 random seeds to reach validation perplexity. I'll wait after accumulating gradients for 16 backward computation. Simulating training on 16 nodes. Okay. Accumulating gradients over multiple forward-backward steps speeds up training by reducing communication between workers, A, and then B, saving idle time by reducing variance in workloads between GPUs. Okay, makes sense. You don't have to do all reduce and wait for everybody to finish. You can just... What happens, can this kind of go out of... Can this go much more asymmetric and then we're still waiting? Okay. Let's see what else they mentioned here. Illustration of how the backward pass in backpropagation can be overlapped with gradient synchronization to improve training speed. Illustration of how backward pass in the backprop can be overlapped with gradient synchronization to improve the training speed. Forward, backward, gradient sync, idle. Okay, so as soon as the first one starts, you start the gradient sync and that speeds up things a bit. I guess that's the logic there, some optimization technique there. So here, looking at the wall time, how much quicker can we squeeze in the loss, minimize the loss with 16 nodes. So the final result on 16 nodes, 85 minutes to get to the state of the art. And here 512 minutes. Okay, and then when training with WMT plus the Oracle data, they squeeze in 0.5 more here, but they lose some performance on English-French direction. Okay, and then some curves comparing, again, these data sets. And then finally, histogram of time to complete one forward and one backward pass for each sub-batch in the WMT training dataset. Sub-batches consist of a variable number of sentences of similar length, such that each sub-batch contains at most 3.5k tokens. Full dataset. And then what's the source length? Bigger or equal than 23, similar to target, and smaller or equal than 27. Okay, so they kind of just what's the thing with those ranges? Did they just label those to show how those times score compared to the other ones, or what? Okay, we'll see later. And that's it. It's a fairly short paper. And then they say the conclusion: we explored how to train state-of-the-art NMT models on large-scale parallel hardware. We investigated low precision computation, very large batch sizes, and larger learning rates our careful implementation speeds up the training of a big transformer model by nearly 5x on the one machine with 8 GPUs. We improve the state of the art to 43.2 versus the 41.5. Training in less than 9 hours on 128 GPUs. Similar thing for German. And then it's additionally improved by adding this paracrawl data. Overall, our work shows the future hardware will enable training times for large NMT systems that are comparable to phase-based systems. We note that multi-node parallelization still incurs a significant overhead. 16-node training is only 10x faster than 1-node training. Future work may consider better batching and communication strategies. Okay. So, only a couple of pages here. 8 pages or less, 7-8 pages. So let's kind of skim through it a bit more. Although I doubt we'll get any special insights here. This is just stuff that's already probably implemented inside of FairSec. Nonetheless, let's go through some parts here. So neural machine translation has seen impressive progress. Again, this is going to be just your usual introduction. Similar sequence-to-sequence models are also applied to other language processing tasks. Oh, little did they know what transformers will do back in 2018. Currently, training state-of-the-art models on large datasets is computationally intensive and can require several days on a machine with 8 high-end GPUs. Scaling to multiple machines introduces new challenges. How do we maintain efficiency in a distributed setup when some batches process faster than the others? I.e. in the presence of stragglers. Why not strangler? What's straggler? A person in a group who becomes separated from the others, typically because of moving more slowly. Straggler. How do larger batch sizes affect optimization and the performance? Well, stragglers primarily affect multi-machine training. Questions about the effectiveness of large batch training are relevant even for users on commodity hardware on a single machine, especially as such hardware continues to improve, enabling bigger models and bigger batch sizes. In this paper, we first explore approaches to improve training efficiency on a single machine. By training with reduced floating point precision, we decrease training time by 65% with no effect on accuracy. Next, we assess the effect of dramatically increasing the batch size from 25K to 40K tokens, a necessary condition for large-scale parallelization with synchronous training. Because I guess 4 times 4, so that's exactly 16 nodes, right? Are they training on 16 nodes? They are, right? They're training on exactly 16 nodes. So going from 25K to 400K is exactly 16x increase, which means they just do 16x data parallelization. They probably shard the model across 8 GPUs. Model sharding more likely than pipeline sharding, and then they do 16x data parallelization, which means they split independent chunks of that big batch sizes of that big batch size, and they put 25K on each of the nodes, and then they just have to do the all reduce across the machines. Okay, so we implement this on a single machine by accumulating gradients from several batches before each update. So we implement this on a single machine by accumulating gradients from several batches before each update. Okay, so that's the gradient accumulation method. We find that by training with large batches and by increasing the learning rate, we can further reduce training time by 40%. So I guess here they're just emulating the setup. When they have a single node, they probably do maybe even as high as 16 times backward passes before doing the final update of the actual parameters, simulating the distributed setup. So they say we find that by training with large batch sizes and by increasing the learning rate, we can further reduce the training time by 40% on a single machine. Finally, we parallelize training across 60 machines and find that we can reduce training time by an additional 90% compared to a single machine. Our improvements enable training a transformer model to the same accuracy as the original transformer paper in just 32 minutes on 128 GPUs and in under 5 hours on 8 GPUs. This same model trained to full convergence achieves a new state-of-the-art. These scalability improvements additionally enable us to train models on much larger data sets. We show that we can reach 29.8 blue on the same test set in less than 10 hours when trained on a combined corpus of WMT and paracrawled data containing 150 million sentence pairs, i.e. over 30x more training data. 30x more training data. 150 million. How much do we currently have in our data set? I think we have quick regression. I think we currently have more than that. We have 280 million sentences. Are those pairs or sentences? Just a second. Yeah, this might not be as representative. I'm not sure. We are certainly in the millions, but this is just primary data set, by the way, so we have mine data either way. Anyhow, let me just put a okay. So these improvements, blah, 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 150 million sentence pairs. Similarly, on the French task, to obtain soda in 8.5 hours. Okay. Related work, we can skip all of that. And let's go to section 3. We run experiments on two language pairs, English-German, English-French. For English-German, they replicate the setup of the transformer paper, which relies on the version 16 training data with 4.5 million sentence pairs. We validate on new test 13 and test on new test 14. We use a vocab of 32K symbols based on a joint source and target byte pair encoding. For English-French, we train on WMT 14 and borrow the setup of these guys with 36 million training sentence pairs. They use these data sets for validation and for test. 40K vocab, again joint source and target factorization. We also experiment with scaling training beyond 36 million sentence pairs by using data from the paracrawl corpus. This dataset is extremely large and noisy with more than 4.5 billion pairs for German and more than 4.2 billion pairs for French. Accordingly, we explore approaches for filtering this dataset in section 4.5. We also reuse the BP vocab built on WMT data for each paracrawl language pair. Okay, we also reuse the BP vocab built on this data. Okay. We measure case-sensitive tokenized blue with multi-blue and the tokenized blue with sacred blue. Okay, just a second. So this dataset paracrawl is super noisy, has a ton more data than WMT, and then they consider filtering it, and then they reuse the BP vocab built on WMT for each of the, okay, assuming it's a similar domain, it will work nicely. And then we measure case-sensitive tokenized blue with this script. Okay, it's just some metrics that they use to track the progress. All results use beam search with width 4, length penalty 0.6. Following was funny. Checkpoint averaging is not used except where specified otherwise. I guess that's usually what people do, is exponential moving average of checkpoint weights. Okay, so we use transformer model implemented in PyTorch in FairSecPy toolkit. All experiments are based on the big transformer model with 6 blocks in the encoder and decoder. Each encoder block contains a self-attention layer. Blah blah blah. We can skip this. This is just implementation of transformer. Residual, apply, blah blah blah. Dropout. This model has 210 million parameters. How small were models back then, man? Like I'm now training 650 million on 2 GPUs here locally. Models are optimized using Madam. Same learning rate schedule as the original paper, transformer paper, i.e. the learning rate increases linearly for 4K steps to 5 or to 1 raised to the power of -3, which is 2x. Okay, so this is the 2x. They reach after the warm-up, they reach a 2x higher learning rate, after which it is decayed proportionally to the inverse square root of the number of steps. They use label smoothing with 0.1 weight for the uniform prior distribution over the vocab. All experiments are run on the DGX1 node with 8 NVIDIA V100 GPUs interconnected by InfiniBand. Oh, back in the days. We use the NCCL2 library and torch distributed. Why is this? If this, how many of the authors were from Google? Okay, just one, David Grangier. Work done while at Facebook. Okay, so this guy was at Facebook as well. So this is basically Facebook's work. Okay, so experiments. We present results for improving training efficiency via reduced precision floating point, training with larger batch sizes, and training with multiple nodes in a distributed setting. Have precision. So this GPU introduced tensor cores that enable efficient half precision floating point computations that are several times faster than the full precision. However, half precision drastically reduces the range of floating point values that can be represented, which can lead to numerical underflows and overflows. This can be mitigated by scaling values to fit into the FP16 range. We perform all forward-backward computation as well as the all reduce, also known as the gradient synchronization between workers in FP16. In contrast, the model weights are also available in the full precision, and we compute the loss and the optimization in FP32 as well. We scale the loss right after the forward pass to fit into the FP16 range and perform the backward pass as usual. After the all reduce of the FP16 version of the gradients with respect to the weights, we convert the gradients into FP32 and restore the original scale of the values before updating the weights. In the beginning stages of the training, the loss needs to be scaled down to avoid numerical overflow, while at the end, when the loss is small, we need to scale it up in order to avoid numerical underflow. Okay, dynamic loss scaling takes care of both. It automatically scales down the loss when overflow is detected, and since it is not possible to detect underflow, it scales the loss up if no overflows have been detected over the past 2K steps. To evaluate training with lower precision, we first compare a baseline transformer model trained on 8 GPUs with 32-bit floating point, our re-implementation, to the same model trained with 16-bit. Note that we keep the batch size and other parameters equal. Table 1 reports training speed of various setups to reach validation perplexity of 4.32 and shows that 16-bit results in 2.9 speedup. So everything remains the same. It's just that they reach in much less steps. They reach the same validation perplexity, was it? Okay, and then so that's first component, FP16, and then training with larger batches. Large batches are a prerequisite for distributed synchronous training, since it averages the gradients over all workers, and thus the effective batch size is the sum of the sizes of all batches seen by the workers. Figure 1 shows that bigger batches result in slower initial convergence when measured in terms of epochs. However, when looking at the number of weight updates, large batches converge faster. These results support parallelization, since the number of steps define the number of synchronization points for synchronous training. Training with large batches is also possible on a single machine, regardless of the number of GPUs or amount of available memory. One simple iterates over multiple batches and accumulates the resulting gradients before committing a weight update. This has the added benefit of reducing communication and reducing the variance in workload between different workers. See the figure 2. Leading to a 36% increase in tokens per second. We discussed the issue of workload variance in more depth. Interesting. So that was my question. How do we make sure that the variance is not skewed? I guess in expectation, because of random processes, you expect them to be roughly the same. By the law of big numbers, more likely than when you have a single one. Okay. So less efficient in terms of epochs, more efficient in terms of optimization steps. Why do we lose the efficiency when training with bigger batch sizes exactly? Okay, so here additionally they do so 16-bit and then 16 gradient accumulation steps. And then they additionally increase the learning rate, and then plus 5k tokens per GPU. We're gonna see what this is in a second. Increased learning rate, similar to Goyal et al. I think these guys trained ResNet like super fast. That was that paper. And then we find that training with large batch sizes enables us to increase the learning rate, which further shortens training time, even on a single node. And finally, memory efficiency. Reduced precision also decreases memory consumption, allowing for larger sub-batches per GPU. We switch from the maximum of 3.5k tokens per GPU to a maximum of 5k tokens per GPU, and obtain an additional 5% speed up. Okay. So you can squeeze in more tokens because they take less memory due to the FP16. This is just kind of free lunch. Table 1 reports our speed up improvements due to the reduced precision, larger batches, learning rate increase, and increased per worker batch size. Overall, we reduced training time from 1,429 minutes to 294 minutes to reach the same perplexity on the same hardware. 5x speed up. Nice. And it's literally the same hardware. Well, here, why do they put P100 here and V100 here? Okay, but they focus, I guess, this was the original paper. Okay, they re-implemented on 8 voltas, and then they just add all this. Okay. So 5x here and then almost 50x on 16 nodes. with just smart algorithmic improvements. Okay, parallel training. Rafael, your comment on, yeah, I believe so. You were making a comment about what? Can you remind me? I was kind of speed rushing through it. Okay, we can continue. Well, it was quite old, don't worry. Okay, awesome. While large batch training improves training time even on a single node, another benefit of training with large batches is that it is easily parallelized across multiple nodes. We run our previous one node experiment over 16 nodes. Table 1 shows that with a Table 1 shows that with a simple synchronous parallelization strategy over 16 nodes, we can further reduce training time from 311 minutes to just 37 minutes. However, the time spent communicating gradients across workers increases dramatically when training with multiple nodes. In particular, our models contain over 200 million parameters. Therefore, multi-node training requires transferring 400 megabytes gradient buffers between machines, because they're using 2 bytes. They're using 2 bytes, and you have to send for all 200 million parameters, you have to send an FP16 information to convey the gradients, and then that's 400 megabytes in this case. Fortunately, the sequential nature of backpropagation allows us to further improve multi-node training performance by beginning this communication in the background while gradients are still being computed for the mini batch. Okay, that's the overlap thingy we saw before. Backpropagation proceeds sequentially from the top of the network down to the inputs. When the gradient computation for a layer finishes, we add the result to a synchronization buffer. As soon as the size of the buffer reaches a predefined threshold, we synchronize the buffered gradients in a background thread that runs concurrently with backpropagation down the rest of the network. Table 1 shows that by overlapping the gradient communication with computation in the backward step, we can further reduce training time by 15% from 37 to just 32. So that's the final step. Okay, that's the overlap. Okay. We illustrate a speed up achieved by large batches in parallel training in figure 4. Nice. Okay, so what's the thing there? Backward. Basically, I think this might be incorrect drawing. I think that as soon as the slowest one starts, so that means here, you can start this yellow window, right? Because at this point of time, at this particular, let me just zoom in, at this particular point of time is when for the last layer of your network, because backward pass goes obviously backwards, all of the 4 machines have computed the gradients and you can start the all reduce. And then as they're progressing down as all of them are doing their backward passes, you can start fetching the already computed gradients for the latter layers and keep on doing the synchronization. That's kind of the logic. You can contrast that with waiting for everybody to finish and then sequentially doing the gradient sync. This is probably just implemented in parsec, but still interesting to think about it. Just have a background thread that immediately grabs everything that's computed and starts the synchronization across the machines. Really, I think the most exciting parts of the machine learning trainings are, I guess, have to do with distributed training, in my opinion. And also just data cleaning, filtering, visualizing. Okay, let's continue. We report the results. They train on the filter version. And they average model parameters from the last 10 checkpoints. Table 2, I guess it's this table, shows reports 29.3 for English German and then English French. A new state of the art for both data sets, excluding settings with additional training data. Okay. Fast parallel training lets us additionally explore training over larger data sets. In this section, we consider paracroll, a recent data set of more than 4 billion sentences for each language pair. Previous work on paracroll considered training only on filtered subsets of less than 30 million pairs. We also filter paracroll by removing sentence pairs with a source target length ratio exceeding 1.5 and sentences with more than 250 words. This is similar to the length filtering we're doing in our pipeline, by the way, guys. We're using the ratio of 9 and we're using 1050 characters on the upside and 5 characters on the lower side. We also remove pairs for which the source and target are copies. Again, this is just deduplication. We're also doing that on the pair level. And this brings the set from 4.6 billion to 700 million. We then train the model on a clean data set to score the remaining 700 million sentence pairs and retain the 140 million pairs with the best average token log likelihood. This is a sort of a language model filtering that's being done all around the place. Pile has been using something similar as well, etc., etc. There's some issues with this filtering, I think. So they train it on the WMT and then they use that to score sentences. So if they're high likelihood, which means they're similar to WMT, then they retain them. So this kind of biases the filtering towards the known domain. I think that's one of the issues. Okay. Next, we explore different ways to weight the WMT and paracroll. Figure 5 shows the validation loss for English-German models. Where is figure 5? Okay, here. Train with different sampling ratios of WMT and filter paracroll. The model with 1:1 ratio performs best on the validation set, outperforming the model trained only on WMT. For English-French, they found that the ratio 3:1 performed the best. Test results are given in table 3. We find that paracroll improves blue, but is not beneficial for French direction, achieving just 42.1 versus 43.2 for the baseline. Okay, fair enough. Validation loss when training on paracroll with varying sampling ratios. BMT only, para only. Wait, isn't it the other way around? 3 to 1 and 1 to 1. So the best thing, this is for English German, okay, and the best thing they got was with equal proportion of both data sets. Okay, analysis of stragglers. In a distributed training setup with synchronized SGD, workers may take different amount of time to compute the gradients. Okay, fair enough. Slower workers or stragglers cause other workers to wait. There are several reasons for stragglers, but here we focus on the different amount of time it takes to process the data on each GPU. In particular, each GPU typically processes one sub-batch containing sentences of similar length, such that each sub-batch has at most n tokens, with padding added as required. We refer to sub-batches as the data that is processed on each GPU worker, whose combination is the entire batch. The sub-batch is processed by a worker may therefore differ from other workers in the following three characteristics: the number of sentences, the maximum source sentence length, or the maximum target sentence length. To illustrate how these characteristics impact training, Figure 6 shows the amount of time required to process the 44K sub-batches in the English-German training data. There is a large variability in the amount of time to process sub-batches with different characteristics. The mean time to process a sub-batch is 0.11 seconds. The slowest sub-batch takes 0.228 seconds and the fastest 0.049. Notably, there is much less variability if we only consider batches of a similar shape. For example, batches where we constrain the target and the source length to be between 23 and 27. So that's the purple one we were wondering in the beginning. Interesting. Makes sense. Because does it make sense? We're not doing this autoregressively, right? Why does this really make sense? If you're doing it, if you're sampling, then of course longer context length translates into longer vol clock time. But if you're just like doing a forward pass, why does this make such a big difference in terms of variance? Number of sentences makes sense, right? Because yeah, I'm not completely sure. I don't have any good intuition why this is the case, honestly. If anybody has an idea, feel free to type it down. Unsurprisingly, constructing sub-batches based on a maximum token budget, as just described, exacerbates the impact of stragglers. Because given just a maximum token budgets, you can have very much different shapes, right? Some may have more sentences of shorter length, some might have less sentences of larger length, longer length. In section 4.2, we observed that we could reduce the variance between workers by accumulating the gradients over multiple sub-batches on each worker before updating the weights. A more direct but naive solution is to design all worker sub-batches with a similar shape. However, this increases the variance of the gradients across batches and adversely affects the final model. Okay, so what they're saying is, okay, we can constrain the shapes of the data for a single step to be similar, but then that causes you, for the next step, you might have much longer sentence lengths or whatnot, and then the variance between these steps will be larger, and that ends up actually hurting the performance. Indeed, we trained the model in this way, then it failed to converge to the target validation perplexity of 4.32. As an alternative, we construct sub-batches so that each one takes approximately the same amount of processing time across all workers. We first set a target for the amount of time a sub-batch should take to process. We first set a target for the amount of time a sub-batch should take to process it. For example, the 19th percentile in figure 6. Which we keep fixed across training. Next, we build a table to estimate the processing time for sub-batch based on the number of sentences and maximum source and target sentence lengths. Finally, we construct each worker's sub-batches by tuning the number of sentences until the estimated processing time reaches our target. This approach improves single node throughput, reducing the training time from 195 to 179. Unfortunately, this is less effective than training with large batches by accumulating gradients from multiple sub-batches on each worker, which was 447 minutes. Moreover, large batches additionally enable increasing the learning rate, which further improves training time. Okay, so all of these heuristics were not really helpful. Ultimately, if I understood what they've done is just big batch sizes, so that means chunk them onto multiple nodes and then just do multiple gradient accumulation steps and let the variance handle itself, not thinking too much about all of this. They're probably still making sure that the sentences in the same batch are of roughly the similar size, I guess. Okay, it's a cool paper. I don't think I've learned anything in particular. Maybe some new ideas about. I didn't really think about this way. How do you guys like the paper? They do very basic filtering for paracrawl. This is interesting. I don't have a really good intuition. Yeah, a lot more digestible than NLLB. NLLB is, I don't know, it's not a hard paper, it's just long paper. There are hard papers that you can read no matter how many times you can't really internalize it until you build it and analyze the code as well. Here you can just read it and understand it. Sub-batches consist of a variable number of sentences of similar lengths. So yeah, so this is the variance that you have when you set the budget to some number of tokens. And then the variance is lower here if you have them of similar lengths. And given that budget, that means they also have similar shape in general. So that makes sense. For the distribution figure, isn't it that having a lot of shorter sentences is faster than less but bigger ones? I mean, the figure doesn't tell us that, right? We don't really know whether on the left here we have shorter lengths, more sentences, or otherwise. It's not intuitive. What I mean, you do a single forward pass with those, right? Yeah, but that might be, you might be misinterpreting, because the plot here on the x-axis we have time, right? We have time, but it's not like it's sorted according to length. You might be confused because this is with 23, 27, and then your brain automatically assigns 23 to the left because this is on the left side. But it might well be that it's the other way around. Ultimately, the part that confuses me is why are we, you're just doing a single forward pass, right? Why is this slowing down the computation? It probably has to do with something much trickier. When you're doing backward pass, shapes of matrices matter because of VRAM memory loading and stuff. So this might be very well some lower level detail. It's not clear if we just abstract away the GPU, the fact that it's not perfect. There is obviously a hierarchy between different memory structures. This might be happening much lower level than anything else. Because on a higher level, right, you just grab that matrix, your batch of data, no matter the shape, and you just push it through the network at the same time in parallel. So I guess the explanation for this might be certainly somewhere lower. Just the matrix shapes do matter when you go to the lower level implementation details. I think that's the thing. It's not clear. Yeah. Okay. So that's the first paper. We are done with the first paper. One empty paper left. Understanding back translation at scale. So we still haven't touched on back translation. Okay, let me see Raphael's DMs. I believe complexity is n squared in sequence length. That's true, but again, the flops matter less ultimately. That's the thing. Than the GPU memory access. And padding tokens can be masked, which makes shorter sequences faster, even if these are padded to the same shape. Yeah, the thing is, you're completely right for the complexity. I mean, that's the case for transformer quadratic complexity in sequence length. But again, it's a trade-off between computation and loading, and so it's not completely clear how it all plays out on the lower level. So your assumption would be that you want to have a lot of short sentences. That might be right. If you mask padding tokens, maybe you can end up with smaller QKV2. I'd have to sit down and draw this on a piece of paper to understand it better. It's hard for me to reason about it honestly on the fly. But still, interesting thing to think about. How is an interesting detail for us might be, I mean, this is more this is getting into the optimization territory, and we're just trying to, for now, replicate the numbers. But it will be fun to see and understand if somebody, Rafael, if you set up the run on your local machine, it will be fun to analyze what exactly FairSec is doing when it comes to these optimizations. Are they trying to get the same sentence lengths in the same batch? Like what's their logic for batching and taking care of the shapes of batches during the training? There might be a fun analysis of FairSec. Yeah, you can put that as a task if you have some time, if that's something that is interesting to you. I'd love to hear a bit more about what FairSec is doing in the background. Okay. Understanding back translation at scale. Awesome. Sounds good. Understanding back translation at scale. Again, as I said, we so far mostly focused on primary bytext. I played a bit with mind as well, but never back translation. So let's see, what is this about? Again, it looks like this is the same set of authors from FAIR. With this guy, I went to Google. So let's skim through the abstract. An effective method to improve neural machine translation with monolingual data is to augment the parallel training corpus with back translation of target language sentences. Okay. Target language sentences. This work broadens the understanding of back translation and investigates a number of methods to generate synthetic source sentences. We find that in all but resource-poor settings, back translation obtained by a sampling or noise beam outputs are most effective. Our analysis shows that sampling or noisy synthetic data gives a much stronger training signal than data generated by beam or greedy search. We also compare how synthetic data compares to genuine bytext and study various domain effects. Finally, we scale to hundreds of millions of monolingual sentences and achieve a new state-of-the-art of 35 blue on the WMT14 English-German test set. This paper is, by the way, let me just see the timelines here. This is 2018. This is August of 2018. And this one was June of 2018. So this came out a bit later from the same authors of the previous paper. Okay. Let's see what's up. Accuracy of models trained on different amounts of back translated data obtained with greedy search, beam search, randomly sampling from the model distribution, restricting sampling over the 10 most likely words, and by adding noise to the beam outputs. So 5 different baselines. Results based on new test 2012 of the WMT English German. Okay, so greedy. So if you obtain the data with greedy versus beam, you would expect beam to be higher quality than greedy. But apparently, as the training data increases, beam is inferior to greedy, which is not intuitive. And then what's top 10? Restricting sampling over the 10 most likely words. So I guess that's the top P. Okay, that's the top P sampling, or top 10 in this case. That performs better than both beam but beam with which size? Beam search with 5. Okay. And by adding noise to the beam outputs, beam plus noise. Interestingly, beam plus noise performs better. Huh. Okay. I'm not sure what they mean by noise to beam outputs. We'll see soon. And then they show some results here. Again, apparently these two perform the best here when adding 24 million synthetic pairs. Let me just see one thing. So according to this plot, we should have the best performer should be beam plus noise, followed by sampling. Here it's vice versa. Here it seems sampling is a bit better. Okay, and then perplexity of source data is assigned by a language model. Data generated by beam search is most predictable. Why is sampling so bad? Perplexity of source data is assigned by a language model. So sampling is very bad. Beam plus noise is very bad in perplexity. Okay, training perplexity per epoch for different synthetic data. We separately report PPL perplexity on the synthetic data and the bytext. Bytext PPL is averaged over all generation methods. Beam, lowest greedy, top 10, beam plus noise, bytext. Okay, these plots don't help a lot. Example where sampling produces inadequate outputs. Mr. President is not in the source. Blank means that a word has been replaced by a filler token. Diese gegensätzlichen Auffassungen von Fairness liegen nicht nur der politischen Debatte zugrunde. These competing principles of fairness underlie not only the political debate. Mr. President, okay. Completely hallucinated. Well, I guess that's sampling. Sometimes you can pick the wrong token, right? And then you just continue doing it. Okay. Blue when adding synthetic data from Beam and sampling to bytext systems with 80K, 640K and 5 million pairs. Okay, let's see. Sampling, Beam, sampling, Beam, sampling. So sampling tends to be better when you have a ton of data, what? And then the trend reverses here. Accuracy on new test 2012. On the A side. On the B side, a mixed domain valid set when growing with real data. Back translated version of the target side. Or back translated new scroll. By text. Okay. DeepL, that's one of the most famous commercial offerings other than Google Translate. But they unfortunately don't cover a lot of languages, maybe only like around 20 something. They don't cover Serbian, for example, which is my native language. DeepL. conclusions. Back translation is a very effective data augmentation technique. Generating synthetic sources by sampling or by adding noise to beam outputs leads to higher accuracy than argmax inference, which is typically used, which is greedy. In particular, sampling and noised beam outperforms pure beam by 1.7 BLU on average for English-German. Both methods provide a richer training signal for all but resource-poor setups. We also find that synthetic data can achieve up to 83% of the performance attainable with real bytext. So that means if you just train on back translated without the original bytext, I guess. So it's kind of lower quality, but if you add it, it's complementary. If you add the back translated data to primary data, then you get complementary results and better performance. But in and of itself, it's lower quality because it's noisy. Finally, we achieve a new state-of-the-art result of 35 BLU on the WMT14 by using publicly available benchmark data only. In future, we would like to investigate an end-to-end approach where the back translation model is optimized to output synthetic sources that are most helpful to the final forward model. Okay. Let's skim through this. I don't have a great understanding. It's not super clear what's the main takeaway, just skimming it like this, other than, hey, back translated data seems to help for high resource languages, but not so for low resource languages. That's the single bullet point that kind of stuck in my mind. Let's read the abstract again. Let's start from here. So an effective method to improve NMT translation with monolingual data is to augment the parallel training corpus or bytext with back translation of target language sentences. This work broadens the understanding. Why target? Why not source? That's the first question. Why not just, do you even care? Like you have one side, you want to create the bytext. Why focus on target? That's the first question I have here. This work broadens the understanding of back translation and investigates a number of methods to generate synthetic source sentences. So they focus on given target, they translate into source. But why? Why is that? Why does that have to be like that? We find that in all but resource poor settings, back translations obtained by sampling or noise beam outputs are the most effective ones. Our analysis shows that sampling or noisy synthetic data gives a much stronger training signal than data generated by beam or greedy. We also compare how synthetic data compares to genuine bytext and study various domain effects. Finally, we scale to hundreds of millions of monolingual sentences and achieve a new state-of-the-art. Okay. So machine translation relies on the statistics of large parallel corpora, i.e. datasets of paired sentences in both the source and target. However, bytext is limited and there is a much larger amount of monolingual data available. Monolingual data has been traditionally used to train language models, which improved the fluency of statistical machine translation. In the context of NMT, there has been extensive work to improve models with monolingual data. Well, even NLLB used this, right? NLLB does this multitask training where you do translation during the training, but also you force your encoder to basically do bird style training on monolingual corpus for the source data. So that's something that NLLB has been using as well, including a language model fusion, back translation, dual learning. This might be what I just described. These methods have different advantages and can be combined to reach higher accuracy. We focus on BT, which operates in a semi-supervised setup where both bilingual and monolingual data in the target languages are available. Again, target language, and then they back translate into source. I guess that's why it's called back translation, but you can kind of go both directions. I mean, well, actually, let me think. Because we know, yeah, you do want to have human written target, right? Because when you translate using this NMT system, it's gonna be lower, it's gonna be more noisier. So you actually do prefer to have noisy source, but if you can from noisy source translate into the right target, then that's better than going from human written source into target. So in that sense, it actually makes sense when I think about it. Okay, so back translation first trains an intermediate system on the parallel data, which is used to translate the target monolingual data into the source language. The result is a parallel corpus where the source side is synthetic machine translation output, while the target is genuine text written by humans. The synthetic parallel corpus is then simply added to the real bytext in order to train a final system that will translate from the source to the target. Although simple, this method has been shown to be helpful for phrase-based translation, NMT, as well as supervised MT. In this paper, we investigate back translation for NMT at the large scale by adding hundreds of millions of back translated sentences to the bytext. Our experiments are based on strong baseline models trained on the public bytext of the WMT competition. Based on the strong baseline models trained on the public bytext. Okay, we extend previous analysis of back translation in several ways. We provide a comprehensive analysis of different methods to generate synthetic source sentences, and we showed that this choice matters. Sampling from the model distribution or noising beam outputs outperforms pure beam search, which is typically used, by 1.7 BLU on average across several test sets. Our analysis shows that synthetic data based on sampling and noise beam search provides a stronger training signal than synthetic data based on argmax. Again, that's greedy. We also study how adding synthetic data compares to adding real bytext in a control setup, with the surprising finding that synthetic data can sometimes match the accuracy of real bytext. Our setup achieves, I'm highly suspicious of that claim. That probably means that their bytext is of shitty quality as well. Our best setup achieves 35 BLU by relying only on public WMT bytext as well as 226 million of monolingual sentences. This outperforms the system of DeepL by 1.7 BLU, who train on large amounts of high-quality non-benchmark data. The fun fact about DeepL is it was actually started by a guy from Brain, I think, back a long time ago. Back in like 2007, they were called Lingui, and then they rebranded as DeepL. But they have a very, very long history in machine translation. They used to be like they have an online dictionary, so that was their first business. They've collected a ton of data, so they have a lot of proprietary data that they've then used after the arrival of Transformer back in 2017 to gain an edge over competitors. So they're really good. They're actually better than Google Translate for many of the languages that they support. They're kind of the best player in the game. Okay. Related work, we can skip this section. Let's go to section number 3. Back translation typically uses beam search or just greedy search to generate synthetic source sentences. Both are approximate algorithms to identify the maximum a posteriori output. i.e. the sentence with the largest estimated probability given an input. Beam is generally successful in finding high probability outputs. However, map prediction can lead to less rich translations, since it always favors the most likely alternative in case of ambiguity. This is particularly problematic in tasks where there is a high level of uncertainty, such as dialogue and story generation. We argue that this is also problematic for a data augmentation scheme such as back translation. Beam and greedy focus on the head of the model distribution, which results in very irregular synthetic source sentences that do not properly cover the true data distribution. As alternative, we consider sampling from the model distribution, as well as adding noise to Beam search outputs. First, we explore unrestricted sampling, which generates outputs that are very diverse but sometimes highly unlikely. So that's the Mr. President sampling we saw before. Second, we investigate sampling restricted to the most likely words, which is top P. At each time step, we select the K most likely tokens from the output distribution, renormalize, and then sample from this restricted set. This is a middle ground between map and... Wait, what's the difference between top P and top K? I might have confused the two. Top P versus top K. Oh yeah. It's just for top P you set the probability mass, and using that mass you grab the K tokens from which you sample. Top K is actually the one where you pick K most likely tokens and you sample from them, if that makes sense. So if you have the whole distribution across your output tokens, top P would be, say, hey, I want 90% of the distribution weight. So you grab whatever that is, and then you sample from those tokens. Top K literally says, hey, I want the K most likely ones, and then I sample from them. I renormalize such that they have 100%, and then I sample. So this is top K, not top P. I've been misusing the terminology. Anyway, just a small digression there. So this is a middle ground between map and unrestricted sampling. As a third alternative, we apply noising to Beam search outputs. Adding noise to input sentences has been very beneficial for the autoencoder setups, which is inspired by denoising autoencoders. In particular, we transform source sentences with three types of noise. Deleting words with probability 0.1, replacing words by a filler token with probability 0.1, and swapping words, which is implemented as a random permutation over the tokens drawn from the uniform distribution but restricted to swapping words no further than 3 positions apart. Okay, so they mess up the target sentences, and then they do the Beam search. Okay. Interesting. Experimental setup section, data sets. The majority of our experiments are based on data from the WMT English-German news translation task. We train on all available byte text, excluding the paracrawl corpus, and remove sentences longer than 250 words. We've seen the same numbers in the previous paper, by the way, as well as sentence pairs with a ratio exceeding 1.5, and same in the previous paper again. This results in 5.18 million sentence pairs. For the back translation experiments, we use the German monolingual news scroll data distributed with the WMT18, comprising 2 to 6 million sentences after removing duplicates. We tokenize all the data with Moses tokenizer and learn a joint source target byte pair encoding with 35K tokens. Okay. We develop all data. When I say all data, that means bytext plus the monolingual, I guess. We developed on news test 2012, and then report final results. We also ran experiments on the larger French task. Okay. Sacred blue. Okay, nothing super informative there. Model and hyperparameters. Again, same thing as in the previous paper. Label smoothing, DGX small machine, InfiniBand, 60 machines, 30K synchronous updates, same library for distributed compute and CCL from NVIDIA, FP16, beam size 5, no length penalty. Okay, results. Our evaluation first compares the accuracy of back translation generation models and analyzes the results. Next, we simulate a low resource setup to experiment further with different generation methods. We also compare synthetic bytext to genuine parallel data and examine domain effects arising in back translation. Okay, we also measure the effect of upsampling bytext during training. So that means artificially going more through that subset of data than the other parts, like weighting. And finally, we scale to a very large setup of up to 226 million monolingual sentences and compare to previous research. Okay, synthetic data generation methods. We first investigate different methods to generate synthetic source translations given a back translation model, i.e. a model trained in the reverse language direction. We consider two types of map: greedy, beam with beam 5. Non-map methods include unrestricted sampling, restricted sampling to the k highest scoring outputs at every time step with k equals 10, as well as adding noise to the beam outputs. So now what confused me here is they are saying we add noise to the beam outputs. But as far as I understood from before, it's that they are adding noise to the target sentences first, like deleting, replacing, swapping, all of that, and then they do translation. I'm not sure what they're saying here. What does adding noise to the beam outputs mean? Do they, okay, so they maybe keep the hypothesis and they start adding noise to the hypothesis while doing the beam, but it's not clear, not completely clear what exactly they do. Restricted sampling is a middle ground. I think that was source. Can you check that again? Hey Adib. Yeah, we're gonna find out what exactly they do, I think, but you can't randomize the source because you don't have the source in this example, right? You're trying to sample the source. So you start from target. So you can either mess up the target by adding noise, or you can start translating and then the intermediate hypothesis, you add noise to them. They probably try both approaches. Let's see what they say. Restricted sampling is a middle ground between beam and unrestricted. It is less likely to pick very low scoring output but still preserve some randomness. Preliminary experiments with top 5, 20, and 50 gave similar results to top 10. We also vary the amount of synthetic data and perform 30K updates during training for the bytext only. 50K updates when adding 3 million synthetic sentences. 75k updates for 6 million and 12 million sentences, and 100k updates for 24 million. Wait, we also vary the amount of synthetic data and perform 30k updates during training for the by text only. Okay, so they have to increase the number of updates, obviously, as they're adding more and more synthetic data. For each setting, this corresponds to enough updates to reach convergence in terms of held out loss. In our 128 GPU setup, training of the final models takes 3 hours and 20 minutes. For the by text only, 7 hours 30 for 6 million and 12 million, and 10 hours and 15 minutes for 24 million. During training, we also sampled the by text more frequently than the synthetic data, and we analyze the effect of this in more detail later. Okay, figure 1 shows that sampling and beam noise outperform the map methods by 0.8 to 1.1 blue. Sampling and beam noise improve over by text only by between 1.7 and 2 in the largest data setting. Okay, so it's 2 between these 2 points, 23.5 and 25.5. Restricted sampling top 10 performs better than beam and greedy, but is not as effective as unrestricted or beam plus noise. Table 1 shows results on wide range of test sets. Sampling and beam noise perform roughly equal, and we adopt sampling for the remaining experiments. So they end up using sampling, which is something we can understand easily. Okay. And again here sampling. Okay, so this was the reversal we saw that I was wondering about in the beginning. So they just pick sampling. Okay. The previous experiment showed that synthetic source sentences generated by sampling and beam with noise perform significantly better than those obtained by pure map. Why is this? Okay. Beam search focuses on very likely outputs, which reduces the diversity and richness of the generated source translations. Adding noise to beam outputs and sampling do not have this problem. Noisy source sentences make it harder to predict the target translations, which may help learning. Similar to denoising autoencoders. Yes, okay, that makes sense. Sampling is known to better approximate the data distribution, which is richer than the argmax model outputs. Therefore, sampling is also more likely to provide a richer training signal than argmax. To get a better sense of the training signal provided by each method, we compare the loss on the training data for each method. We report the cross-entropy loss averaged over all tokens and separate the loss over the synthetic data and the real bytext data. Specifically, we choose the setup with 24 million synthetic sentences. At the end of each epoch, we measure the loss over 500k sentence pairs, subsampled from the synthetic data, as well as an equally sized subset of the bytext. For each generation method, we choose the same sentences except for the bytext, which is disjoint from the synthetic data. This means that losses over the synthetic data are measured over the same target tokens because the generation method only differ in the source tokens. We found it helpful to upsample the frequency with which we observe the bytext compared to the synthetic data, so that's the weighting we mentioned, but we do not upsample for this experiment to keep conditions as similar as possible. We assume that when the training loss is low, then the model can easily fit the training data without extracting much learning signal compared to data which is harder to fit. Okay. Figure 2 shows that, we'll read this again, I'm a bit confused here what's going on. Figure 2 shows that synthetic data based on greedy or beam is much easier to fit compared to data from sampling. Top 10, beam plus noise, and the bytext. In fact, the perplexity on beam data falls below 2 after only 5 epochs, meaning that it's not very diverse, I guess. That's the figure 2. Except for sampling, we find that the perplexity on the training data is somewhat correlated to the end model accuracy. Okay, see figure 1. And that all methods except sampling have a lower loss than real bytext. These results suggest that synthetic data obtained with argmax does not provide as rich a training signal as sampling or adding noise. We conjecture that the regularity of synthetic data obtained with argmax is not optimal. Sampling and noised argmax both expose the model to a wider range of source sentences, which makes the model more robust to reordering and substitutions that happen naturally, even if the model of reordering and substitutions through noising is not very realistic. Next, we analyze the richness of synthetic outputs and train a language model on real human text. And score synthetic source sentences generated by beam search, sampling, top 10, and beam noise. We hypothesize that data that is very regular should be more predictable by the language model and therefore receive low perplexity. We eliminate the possible domain mismatch effect between the language model training data and the synthetic data by splitting the parallel corpus into 3 non-overlapping parts. On 640k sentence pairs, we train a back translation model. On 4.8 million sentence pairs, we take the source side and train a 5 gram KN model, and on the remaining 450k, we apply the back translation system using beam, sampling, and top 10. For the last set, we have genuine source sentences as well as synthetic sources from different generation techniques. We report the perplexity of our language model on all versions of the source data in table 2. The results show that beam output receives higher probability by the language model compared to sampling, beam noise, and real source sentences. This indicates that beam search outputs are not as rich. This lack of variability probably explains in part why back translation from pure beam provides a weaker signal than alternatives. Closer inspection of the synthetic sources reveals that sampled and noised beam outputs are sometimes not very adequate. Much more so than map outputs. Example, sampling often introduces target words which have no counterpart in the source. This happens because sampling sometimes picks highly unlikely outputs which are harder to fit. Okay, so sampling has the highest perplexity, bytext, and then all the other ones. Okay, this section was fairly confusing. You sample according to the output distribution. So that means how likely is the token, that's how likely you'll sample it, as opposed to greedy. For greedy, if you have like a distribution, you always pick the token with the max likelihood, with the maximum probability. For sampling, Tokens are sampled depending on how likely they are. Restricted one is stop K. They didn't use stop P here. So, okay, so high level conclusion is go sampling, because sampling, the data that was sampled using sampling approach, even though it's not, sometimes it's noisy because you introduce some words like Mr. President, as we saw, but despite that, it covers the data distribution in a better fashion. So then later, when the model is learning how to translate from those source sentences to target, it actually helps the learning because it's kind of a source of noise and you're trying to predict the right target. So it intuitively makes sense, actually. I probably have to read section 5.2 once more just for this to kind of settle down. Okay, a couple more pages and we're done here. And then we can maybe revisit. We can revisit section 5.2 because there was just a ton of information. But intuitively it makes sense what they're trying to say. Yeah, no worries. Low resource versus high resource setup. Okay, so it was all based on the large bilingual corpus models, where you can use those already fairly powerful systems to do the back translations. However, in resource poor settings, the back translation model is of much lower quality. Are non-map methods still more effective? To answer this question, we simulate such setups by subsampling the training data to either 80K pairs or 640K pairs, and then add synthetic data from sampling and beam search. We compare these smaller setups to our original 5.2 million sentence PyText configuration. The accuracy of the back translation system steadily increases with more training data, obviously. They measure 13.5 blue on 80K, 24.3 for 640K, and 28.3 for 5 million. Okay. Figure 3 shows, these are also some good numbers for us, right? So like with 5 million sentence pairs for a target language, you can expect some improvements, although they're using smaller models, so a lot of things will be different for us. Okay, figure 3 shows that sampling is more effective than beam for larger setups, while the opposite is true for resource poor. This is likely because the back translations in the 80K setup are of very poor quality. So I guess even beam at that point is introducing a ton of noise, because the model itself is introducing a ton of noise. And the noise of sampling and beam noise is too detrimental for this brittle low resource setting. When the setup is very small, the very regular map outputs still provide useful training signal, while the noise from sampling becomes harmful. Okay, again, this makes sense in that same light. You want to introduce noise to your source, but not too much. If you already have the model that's like sucks and it's introducing noise, and then if you additionally add sampling, that's just like doubling the noise, quote unquote doubling. Domain of synthetic data. Next, we turn to two different questions. How does real human bytext compare to synthetic data in terms of final model accuracy? And how does the domain of monolingual data affect the results? To answer these questions, we subsample 640K sentence pairs of the bytext and train a back translation system on this set. To train a forward model, we consider 3 alternative types of data to add to this 640K training set. Just a second. So to train a forward model, we train 3 alternative types of data. We either add the remaining parallel data, okay, that's kind of should be the gold standard. The back translated target side of the remaining parallel data. Okay, so that's the synthetic. And the back translated new scroll data. I'm not sure what this is. The back translated data is generated via sampling. This setup allows us to compare synthetic data to genuine data because since BT text and byte text share the same target side. It also allows us to estimate the value of BT data for the main adaptation since the new scroll corpus is pure news, whereas the byte text is a mixture of Europarl and common crawl with only a small news commentary portion. To assess domain adaptation effects, we measure accuracy on 2 held out sets, news test, a held out set of the WMT, which is a mixture of Europarl, common crawl, and the small news commentary portion. Okay. Figure 4 shows the results on both validation sets. Most strikingly, BT News performs almost as well as byte text on news test. Figure 4a. Okay, because even though it's lower quality, it compensates for the fact that it's closer to the domain, to the target domain that we're testing on. And improves the baseline by 2.6 blue. BT byte text improves by 2.2 blue, achieving 83% of the improvement with real byte text. This shows that synthetic data can be nearly as effective as real human translated data when the domains match. Okay. But the domains do not match, right? Because we back translate only this one matches the domains. Okay, whatever. This shows that synthetic data can be nearly as effective, blah, blah, blah. Figure 4b shows the accuracy on valid mixed, the mixed domains valid set. The accuracy of BT news is not as good as before since the domain of the BT data and the test set do not match. However, BT news still improves the baseline by up to 1.2. On the other hand, BT byte text matches the domain of valid mixed and improves by 2.7. This trails the real byte text by only 1.3 blue and corresponds to 67% of the gain achieved with real. In summary, synthetic data performs remarkably well, coming close to the improvements achieved with real byte text for newswire test data, or trailing real byte text by only 1.3 blue for valid mixed. In absence of a large parallel corpus for news, back translation therefore offers a simple yet very effective domain adaptation technique. Okay. Upsampling the byte text. We found it beneficial to adjust the ratio of byte text to synthetic data observed during training. In particular, we tuned the rate at which we sample data from the byte text compared to synthetic data. For example, in a setup of 5 million byte text sentences and 10 million synthetic ones, an upsampling ratio rate of 2 means that we double the frequency at which we visit byte text, i.e. training batches contain on average an equal amount of bytext and synthetic data as opposed to 1/3 of bytext and 2/3 of synthetic. Figure 5 shows the accuracy of various upsampling rates for different generation methods in a setup with 5 million bytext sentences and 24 million synthetic sentences. Beam and Greedy benefit a lot from higher rates, which results in training more on the bytext data. This is likely because synthetic Beam and Greedy data does not provide as much training signal as the bytext, which has more variation and is harder to fit. On the other hand, sampling and beam noise require no upsampling of the bytext, which is likely because the synthetic data is already hard enough to fit and thus provides a strong training signal. So as you can see, beam and noise do not really benefit beam plus noise, and sampling do not benefit from increasing the bytext, whereas these two do increase, greedy and beam. Okay, this is kind of a different perspective on the same general principle here, and that's that when you have a high quality back translation model, you want to go sampling or beam plus noise. Large scale results. To confirm our findings, we experiment on the WMT where we show results. We augment the large bytext of 35.7 billion sentence pairs by 31 million new scroll sentences generated by sampling. To train the system, we perform 300,000 training updates in 27 hours on 128 GPUs. We do not upsample the bytext for this experiment. Okay, table 4 shows token as blue and table 5 shows the token as blue. To our knowledge, our baseline is the best reported result in the literature for news test to 2014, and back translation further improves upon this by 2.6 blue. Table 4 and 5. Okay. Finally, for English German, they upsample the bytext. Okay. Why such a big difference between German and before we had what? French. With no upsampling, and here we have 16x. Interesting. What's the difference? How much of bytext do we have for German? That's not there. Okay, anyhow. So for comparison, DeepL, a commercial translation engine relying on high quality bilingual data, achieves 33.3 blue. Table 6 summarizes our results and compares to other work in the literature. This shows that back translation with sampling can result in high quality translation models based on benchmark data only. Okay. Okay, I get it, because they have so much more back translated data here, so they have to upsample the bytext much more than for English French. Okay, and then the last section here, describes our entry to the WMT 18, which was ranked number 1 on the human eval. They assembled 6 PACS translation models trained on all available byte text, plus the 226 million new scroll sentences or 5.8 billion German tokens. 4 models used byte text upsample ratio 16, 1 model upsample ratio 32. They differed because we reused models previously trained to tune the ratio. We did not use checkpoint averaging. More details of our setup and data are described there. Okay, this is just for getting the bold numbers, but like ensembling 6 translation models is not something you would ever do, I guess. Show that beam search sometimes outputs source copies rather than target language translations. We replaced source copies by the output of a model trained only on the news commentary portion. This model produced far fewer copies since this dataset is less noisy. So it literally outputs the same thing as the target. I'm not sure what they refer to as a source copy. We used news test 17 as a development set to fine-tune ensemble size and model parameters. Table 7 summarizes the effect of back translation data, ensembling, and source copy filtering. Baseline plus BT, plus ensemble, plus filter copies. Okay. Okay, now the paper makes a bit more sense. Let's reread section 5.2 again. Let's maybe just make a short break, just to stretch the legs a bit, clear up the brain cells, and then we can go through the section 5.2 again, which was a bit more confusing to me at least. If that sounds good, let's do that break. Let me put a note here that I'm off for a small break. 4-minute break, stretching legs, then reading again 5.2. 5.2. Oh, the picture. Okay, guys, catch you in a couple of minutes, 4 to 5 minutes. Let me just put it like here, or a 5-minute break. Okay, catch you in 5 minutes, guys. back again. Let's continue, guys. Let's wrap up the paper. And then let's go and do these other tasks. Prepare Flores 202. Test the apex speed. Let me see how the Stopes is progressing quickly. Let me go to Stopes. It's still running apparently. And wow, that's super slow. 2 hours to process just a single batch here. Yeah, I have to improve this logic somehow, because oftentimes just one of these is taking a ton of time. So there is just a single process here. So what I think I should do is sort directions such that, yeah, I'm gonna do a quick improvement after we're done reading the paper here, so that we don't have to wait for this much anymore. I want to sort directions such as similar size directions are batched in the same batch, because now we're waiting for this one single process, and then later maybe we'll have one more such process, such task, or two more, and that's going to triple the runtime. So there is a simple optimization I can do here to make this faster. Otherwise, this is slowing us down too much. Okay. Section 5.2 again. Let's quickly go through it. Let me just maximize the window. Okay. So, the previous data showed that synthetic source sentences generated by sampling and beam with noise perform significantly better than those obtained by pure map methods such as beam or greedy. Why is this? So again, the high level logic is it covers more of the data distribution. Even though it's more noisy, it's better than the greedy or beam. That's kind of the intuition, because you're sort of doing denoising process later when you're doing forward translations. And that helps the learning. So beam search focuses on very likely outputs, which reduces the diversity and richness of the generated source translations. Adding noise to beam outputs and sampling do not have this problem. Noisy source sentences make it harder to predict the target translations, which may help learning similar to denoising autoencoders. Okay, sampling is known to better approximate the data distribution, which is richer than the argmax model outputs. Therefore, sampling is also more likely to provide a richer training signal than argmax sequences. To get a better sense of the training signal provided by each method, we compare the loss on the training data for each method. We report the cross-entropy loss averaged over all tokens and separate the loss over the synthetic data and the real bytetext data. Specifically, we choose the setup with 24 million synthetic sentences. At the end of each epoch, we measure the loss over 500k sentence pairs subsampled from the synthetic data, as well as an equally sized subset of the bytetext. For each generation method, we choose the same sentences, except for the bytetext, which is disjoint from the synthetic. This means that losses over the synthetic data are measured over the same target tokens, because the generation methods only differ in the source sentences. Okay, this is just super confusing text, but we found it helpful to upsample the frequency with which we observe the bytetext compared to the synthetic data, but we do not upsample for this experiment to keep conditions as similar as possible. We assume that when the training loss is low, then the model can easily fit the training data without extracting much learning signal compared to data which is harder to fit. Figure 2 shows that synthetic data based on greedy or beam is much easier to fit compared to data from sampling, top 10, beam plus noise, and the bytetext. So figure 2 shows that exactly. So we have sampling, byte text, and then all of them, beam and greedy at the bottom, being easiest to basically fit. In fact, the perplexity on beam data falls below 2 after only 5 epochs. Except for sampling, we find that the perplexity on the training data is somewhat correlated to the end model accuracy, and that all methods except sampling have a lower loss than real byte text. These results suggest that synthetic data obtained with argmax inference does not provide as rich a training signal as sampling or adding noise. We conjecture that the regularity of synthetic data obtained with argmax is not optimal. Sampling and noised argmax both expose the model to a wider range of source sentences, which makes the model more robust to reordering and substitutions that happen naturally, even if the model of reordering and substitution through noising is not very realistic. Next, we analyze the richness of synthetic outputs and train. So the part that I don't understand is exactly, I don't understand the exact setup. I understand the concept they are mentioning here, but not the exact details. Training perplexity. Do they fit an LLM to this back translated source sentences data, or what? Like, that's the part that's not clear. Do they train from scratch or what? Like, is that the thing they're doing? Like, they take the target sentences, they back translate using these 5 different methods, and then they take that source sentence data set and then fit an LLM and then look at the loss and what's easier to learn. And so because the argmax methods are basically narrower domain, it's easier to fit that data. That's how I'm understanding it, but I'm not sure whether that's the exact setup. Next, we analyze the richness of synthetic outputs and train a language model on real human text and score synthetic source sentences generated by beam search, sampling top 10 and beam plus noise. We hypothesize the data is very regular, should be more predictable by the language model and therefore receive low perplexity. Okay, similar experiment, just a bit different setup, I guess. We eliminate a possible domain mismatch effect. I was about to sneeze. Snap. We eliminate the possible domain mismatch effect between the language model training data and the synthetic data by splitting the parallel corpus into 3 non-overlapping parts on 640,000 sentence pairs. We train a back translation model. On 4.1 million sentence pairs, we take the source side and train the language model. By the way, I keep on using LLM, but what I want to say is language model. On the remaining sentences, we apply the back translation. Okay. So 3 different splits. 1 to train the LLM on byte text. 1 to train back translation, and then they translate the 450,000 using beam, sampling, and top 10. For the last set, we have genuine source sentences as well as synthetic sources from different generation techniques. Okay. We report the perplexity of our model on all versions of the source data in table 2. The results show that beam outputs receive higher probability by the language model compared to sampling, beam plus noise, and real source sentences. This indicates that beam search outputs are not as rich as sampling outputs or beam plus noise. This lack of variability probably explains in part why back translation from pure beam search provides a weaker training signal than alternatives. Closer inspection of the synthetic sources reveals that sampled and noised beam outputs are sometimes not very adequate, much more so than map outputs. For for example, sampling often introduces target words which have no counterpart in the source. Okay. So again, just two setups to show that the variability of the map-based approaches like greedy or beam, diversity of that data is not as diverse as with these other methods such as sampling or beam plus noise. Okay, this makes sense. So like the takeaway from the paper is back translated data, if we're dealing with higher resource languages, makes sense as an augmentation method. So that means if you can train that back translation model on the initially on your byte text and then use it to back translate the target sentences into the source sentence domain, then if you add that synthetic data to your training data set, you're going to get some improvements. And they show this in multiple ways in this paper. During sampling, are we saving statistics on tokens? I have frequency and using that to sample and subsequently readjust the frequency. No, I mean, sampling is the simplest thing ever. Like sampling, you grab your target sentence, okay? You encode it, and then you start sampling from your decoder. And you basically, at the output of your first token, you get a distribution, and you basically sample according to that distribution by definition. That's how you pick the next token. Then you squeeze in that token as the next one, you do a forward pass, you again get the distribution. So there is no tracking, you don't need to track anything really. You just have to grab the previously sampled token, put it inside as the next token, do a forward pass again, get a distribution, sample the token, feed it in again, and so autoregressively keep on generating the tokens. Okay. We are done with papers. Let me quickly go and optimize the filtering batching logic, and then we can go and do these other tasks. I can point you, if it's helpful, I can point you to some resources, but it's like the most basic thing where I can quickly draw something as well. Yeah, I don't have OneNote on Ubuntu, so that might be a bit harder. But yeah, just Google for like sampling in transformers. You'll find a good blog, I'm sure, if you don't know how it works. Okay, let's go back to Stokes. So again, this is taking too much time for some reason. I think the last time it was faster. Let me just put the breakpoint here. Let's see how we are progressing. So it's working, but it's so slow that it's crazy. 29 million. Oh my god, that's because this dataset is just huge. Oh, are we done? Bro, just remove this. What's up? Let me see we're still here. Okay, so here's one optimization we're gonna do. Yeah, just autoregressive sampling. No, it's literally the same thing. That's what I say in the paper. It's just a sampling approach. I mean, autoregressive sampling is, by autoregressive sampling, people also, that also encompasses potentially greedy. Like it depends on the method you're using to do the autoregressive sampling. Greedy sampling is also sampling, but when somebody says sampling, that means a very particular thing. That means you sample from potentially all of the tokens depending on their probabilities. The unconstrained sampling might be a better, more precise definition. Okay. Coming back here, we have a ton of directions. What we can do is calculate the lengths We can additionally feed in the lengths and use that as the signal to batch the directions. So let's see what's the best way to do that. Let's open up the example config. We have directions. Why not plug in the information about number of tokens per direction, number of sentences per direction, and then use that as the criterion for batching. Let me think. Include the corpora, directions. So currently, if you take a look at this script, we go through the train primary YAML and we just grab directions, but we have no idea how many what's the number of sentences. So let's see how we can change this. Let's see the train primary one. Here's the train primary. While going through train primary, we could just do count lines. So let's do that. Let's create directions that also contains additional piece of information here and use that to prioritize directions. How can we do that? If we go to the extract directions and corpora script, while we are going through this config keys, we basically dismiss all of the information about source. Again, let me just check one thing. Fairsec. In Fairsec we have count lines, and I'm fairly sure we have this count lines function in Stopes as well. Let's find the definition. Count lines. Where is this defined? It's in utils. So let's just use this. Let's basically just use this function. Stopes core utils. Let's see how this is imported elsewhere. Okay, let's do this. Let's go back to our extract script. Where is the extract directions and corpora? Let's import this. And let's now use this to, whoops, let's use this one. Okay, now we have this, we need to extract for the direction. We need to accumulate stuff. Config values, config keys. Okay, directions are here, that's cool. Let's go. Okay. Again, train primary, let me just see, let me open it up on the right here. It's direction followed by a ton of data sets potentially. Okay, fair enough. Let's go here. So for a direction, data sets, then we want to iterate through the data sets. Exactly. And then we want to grab source path and target path. let's count the lines. Exactly. Then put number of lines per. Just a second, let's go to filter. Are we doing this in parallel? When we are doing these filtering jobs, we are going and doing what? We're going here and we grab both the source and the target, and then we iterate through them in parallel. So dataset is gonna give us line is actually a byline, meaning we have both source and target there. So we actually only care about, okay, just counting up ones. So what we need to do is number of sentences for language direction, start with 0. And then here we just need to edit once. Actually, not this. We just need it once. And then we can basically create a dictionary, a language direction, number of sentences, like this. And then we can do basically this. Okay, at the end here we don't even need this, or we can just keep it like that. But basically we want to dump directions. We really want to dump not this, but instead this. Okay, so if we do that, let's run this. With no arguments, let's just run the script. This should work. If I didn't make any stupid mistake, this should work. Let's just double check. Language direction. We grab the corpus, extract source, extract number of lines, just add it once. Maybe we can do assert between source count and target count. Let's do it like that. Let's stop. And then we put a breakpoint here. Let's run this. Let's run. Come on. Come on from the radio. Okay, here it is. And now we can, well, the easiest thing, good morning, SQ. Any insights from the papers you can use? Yeah, we went through 2 papers. Not really. I think I knew all of the high-level insights I already knew. Like the high-level insights are back translation data is useful, and the second is a couple of optimization things like using FP16, data parallelization, overlapping gradient, synchronization with backward passes, a couple of optimization methods from the first paper. Nothing super, nothing I didn't know already, in a way. Okay, so guys, let's sort this dictionary. Sort the dict according to the values, and then okay, fair enough. We grab the items, and then according to this we sort them. Will this give us reverse, or let's see what happens here. Let me create a temporary dictionary here. And let's see how it looks like. So it starts from the biggest ones. Instead of that, I want to actually go reverse false. Okay. And That's good. Let's rerun. This is gonna make sense in a couple of seconds what I'm doing here, because this is gonna be so faster than what we've been previously doing. Okay, dump this. Let me show you the directions YAML now. So here is how it looks like now. And previously, let me see if I can do Ctrl Z. I can't do Ctrl Z. But previously we just had directions, right? We previously had, and you can see it's sorted. Well, it's not sorted. Wait. Something is off here. We're gonna fix it in a second. First, let's just go and Ctrl Z, just return back to the old implementation. This was the old implementation. If we run this, we get hit F5. This is what we get here. Just directions. Now, after we implement this, we end up with this, and now we want to dump this and preserve this same ordering in the file. So just dump the data to the file, and let's see what we get. Okay, so this is what we get. But why is it not obeying what it's sorting according to? Okay, it's alphabetically sorting according to the keys, which I don't want it to do. I just want it to dump it as it is. So let's see how we can force that to happen. Does this dump have some sorting data stream dumper? Let's see. YAML dump Python. This is PyYAML. These are all different packages. Bro, I don't want to use PyYAML. Just show me the PyYAML. Just show me the regular YAML. I want to find the reference. No sorting. Let's see whether this works. Let's see whether this works. Run. It did not fail, so then that means it worked. Awesome. That's it, guys. That's it. So let me now show you how this is gonna play out. Okay. Yeah, I mean, we are dealing with parallel corpuses because we're training machine translation systems. Not sure what exactly are you asking. Like 20 directions with, yeah. Those 20 directions have, because they come from the same, they are only covered by a n-way parallel corpus, like probably NLLB seed or something. That's why they all have the same number of sentences. Let's go to filtering now. So let's think of a logic that makes sense here. I have a couple of ideas. The easiest one is just keep it at 16 again. Just grab them at size 16 and not think too much. And that's probably, I think, good enough. The easiest implementation is, I think, good enough. I'm not sure how many processes I can start without causing issues, but I think 16 is a reasonable number. You can probably try even more, but like I think 16 makes sense. Okay. So now we actually don't have to do anything, right? We just need, I can just remove this to do, because we are going to grab the old directions. We're going to grab all of the directions and then go through them. We actually, because we sorted, okay, let's just extract. Okay, I'm gonna stop the filtering now. I'm gonna delete everything we had. Just delete everything. And let's see how much faster this is gonna go. Either way, we won't be blocked by this because we'll be doing other stuff. So let's see, what do we get here? We just have to extract directions, but let me see what's the format. So set the filtering config from long.json and kick it off again. Okay, directions. Okay, exactly. I want to see what this is. Yes. So ultimately we want to disregard. We just want the keys in the same order. We just want to grab the keys. Safe load, and then directions are actually equals directions keys. Let's stop this. Let's rerun and let's make sure they are in the same order as what we had in the file. So keys, and we also have to make it a list. We have to make it a list, but let's see whether, okay, directions, and then we copy directions there once, and then we do this. Okay. Well, we don't even have to do this because later config directions are going to be set down there. Okay. Directions. Here is the list. Let's see. Let's rerun with list. Hit run again. Yeah, no worries, SQ. So directions, here they are. Let's compare that with what we have in the file here. Just reopen this on the right side. Put it there. And let's compare. Make sure these are the same. So African English, English Latin SOT, SSW. And then the 15th is Arab Hindeva, and there Arab Hindeva, same thing. And then 17th Arab Indonesian. For us it's Arab Indonesian. Looks the same. 88 is English Latin GRN. For them, 89 is English Latin GRN. Okay, awesome, guys. This is it. That's the whole logic. So what we're doing now is we're running these in parallel. We grab the first 61, and obviously these ones are going to finish very quickly, and then they'll wait for these ones. So these are going to be the bottleneck. And then next up, all of these are going to be pretty much the same time, and same here, and same here, and then maybe these ones are going to slow down these ones, and then same, and then same, same, roughly same, roughly same, roughly same, roughly same there, until the very end, where these four is going to dominate the execution. So I think now this is going to be like so much faster. Let's see just how much. I expect filter out new to be populated fairly quickly for these first initial batches. Let's just see whether that makes sense. Let me remove this condition. Let me see whether I made any weird changes here that we don't want. So filter, where is the, why don't I see the git diff? Yeah, just nothing really complicated, right? Very simple logic, because it's always the bottleneck is the slowest job, and before we had a heterogeneous mix, and so sometimes it was very suboptimal. Let's see. Where is the diff, man? Why don't I see the diff? Okay, if you don't want to tell me, then I'm gonna go and just do copy path. Let's navigate there. Let's go to Stopes. Let's just do a diff tool in meld, and let's just find filtering. Okay, so the only thing we've done here is, well, the only thing we've done is on the actual config side, and here we just grab the keys. That's it. Okay. Let's kick this off and let's see how fast it goes now. Like, I literally expect this to be done. Oops, batch 0 to batch 1. What? Something is off here. All directions. Oh. I made a mistake. I do have to either grab directions here or well, we don't even need all directions. I mean, this can be called all directions. And then we don't need this. And then, so these are the all directions. And we go through those and we just patch into here. Okay. Just a small bug I had there. Let's go. Let's see. We can obviously delete this. This should be fairly fast. Like these should be just be running and then very quickly wrapping up. As soon as they start, there is some obviously overhead for them to start, but as soon as they start, they're gonna wrap up very quickly. And as you can see here, they are done, and we are up for the next batch. And here's the next batch. So we are already dealing with, we are already at the phase where, let me just delete this. I thought I deleted it. Delete. Okay. So we are already dealing with, we're already almost at the stage where we're processing the first 32 directions. And we have around 290 something, but we're gonna get very quickly to this last batch. And the last batch is gonna be slow. The last batch might take a bit while. So here we are already 32 to 48, so like very fast. This optimization was very, very good. I should have done it before. It was very simple. So until we're doing that, let's go and see what's up with Flores 202. Let's prepare it, and then we can use it for tracking the progress during training. And then we can go and handle Apex profiling. Okay, back to Farsec. Let's go back to Farsec. Let's go to the download parallel corpora. That's where I've added the Flores 202. Let's just make sure that first of all, I'd love to rename this to train datasets. And we need to add eval datasets. What? Okay, I probably messed up something. Oh my god. Okay, okay, I messed up filtering by renaming the. Okay, I messed up filtering by renaming that thing, but it doesn't matter. It was very fast either way. That's a good learning. Don't change names unless you have to. Unexpected things might start happening. Let's go back here. The reason I wanted to do that is because I need to handle Flores, download data, find the download data script, config, download primary data. Let's put this to data sets. Let's put this to train data sets. And then let's add eval datasets. And now let's go to download. Let's add additional directory. Well, we can leave it at E, I don't know. Okay. exactly. And then these should go here. Okay. These should go here, and now we can go and retrigger filtering. Let's go back to Stopes. Let's recompute populate data config. We have to first update its launch JSON. Populate data config. We need to rename this to train datasets. And now we can rerun it. Let's go and rerun it. Let's go and set populate data config. Run this. Hit F5. Train primary. Here it is, updated with the new directory. And now we have to rerun this. Using this script, we populate the new, this will not change actually, so I didn't have to do it really. Directions will not change, included corpora will not change. So as you can see, 279 directions. Okay guys, and now let's go to filter, and let's not change the name, otherwise we'll just crash the filter. So again, this is clean again, and go to filter, set the filtering config and run it. Let's make sure it's not crashing for some stupid reason. Looking good. We're first handling the simplest ones, and then let's just make sure this finishes and starts the next patch. There are no issues. It doesn't look like there are any issues, but let's make sure that's the case. And then we can attempt back to setting up Flores 202 for eval. Okay, looking good. We're done with the first one. Let's continue. We are here. This can now, truth be told, be uncommented and checked in like this. And Flores 202. Well, actually for testing now we have to kind of comment out everything either way. Let's just make sure we're not running this, and then let's just enable this one, but later we're gonna comment out everything. Okay, Flores 202. Let's see what happens if we just run this as it is. Nothing happens because I have a wrong file. I have to use the download primary data config and then rerun the script. Download with the download config. Let's get here, hit F5. We have eval dataset. We have underneath it Flores 202, and then this. So ideally, what I want is to remove this intermediary directory, just have Flores 200 here, and then dev and dev test. So I think in the paper they test on dev test. What did they use dev for? Let me see how they exactly use dev and dev test. Let's see how dev test is mentioned. Okay, just statistics. Okay. Okay, so they use dev test there. Why not dev? To find the ratio margin. We look for best performance on the development set and report on dev test. Okay. Yes, all of their evals are on dev test. Okay. So we'll use dev during the iteration phase and then just report results on dev test. Do we care about this? Do we really care about this? So it's literally where they found it, where they found the sentence from. Do they have some type of a line here? Okay, URL, domain, topic, has image or not, has hyperlink or not. Okay, we don't need this. So what we can do is once we download this to the download path, and once we extract it, we end up with this. Okay, this is a n-way parallel corpus. All of them have the same number of sentences. 997, 997, 997 in different languages. So what we can do is, by the way, let's quickly skim just out of curiosity. Let's go through some of the examples. Let's see what type of sentences. It's from Wikipedia domain, Wikimedia domain, however they, I'm not sure what's exact difference. A, B, C, D, E, where is English? English, Latin, okay. On Monday, scientists from the Stanford University School of Medicine announced the invention of a new diagnostic tool that can sort cells by type. A tiny printable chip that can be manufactured using standard inkjet printers or possibly about $1 US each. Lead researchers say this may bring early detection of cancer, tuberculosis, HIV, and malaria to patients in low-income countries where the survival rates for illnesses such as breast cancer can be half those of richer countries. The Jas 39C Gripen crashed onto a runway at around 9:30 a.m. local time and exploded, closing the airport to commercial flights. The pilot was identified as squadron leader Dilokrit Patavi. Local media reports an airport fire vehicle rolled over while responding. 28-year-old Vidal had joined Barça 3 seasons ago from Sevilla. Since moving to the Catalan capital, Vidal had played 49 games for the club. The protest started. Okay, it seems like it's almost like every two sentences are different from different topic. The protest started around 11 local time, UTC+1 on Whitehall, opposite the police guarded entrance to Downing Street, the Prime Minister's official residence. Just after 11, protesters blocked traffic on the northbound carriage in Whitehall. At 11:20, the police asked the protesters to move, blah, blah, blah. Around 11, the protest moved up. So again, this is 4 sentences related to the same topic, same article. Nadal's head-to-head record against the Canadian is 7-2. He recently lost against blah blah, Nadal. Okay, let's see what else here. Looks like news almost, not like Wikipedia. Humans can be affected by breathing affected water taken into the air by wind and waves. Fish often die because of the high concentrations of toxins in the water. Okay, so that's kind of the sort of sentences that are in here. A triceratops could have used its strong beak to strip off the leaves before eating the trunk. About 3,000 years later, in 1610, Italian astronomer Galileo Galilei used a telescope to observe that Venus has phases just as the moon does. European Turkey includes 3% of the country. Okay, I was just curious about how that looks like. Now let's see. What I want to create out of this is 2 data sets on the top level, and then we can organize them by language directions that we care about. So let's prepare. Let's see how we can prepare this. Okay. Now we do OS remove. Exactly. Okay. We remove those 3 files, and then we go to dev. We prepare it for directions that we care about. So I guess eval directions. there is over 40,000 possible directions, which means we don't want to go fully blown there. Let's pass in a list of strings, basically. And then exactly. So for both of them, we go through the directions, and then we grab the source and the target by splitting. And then given this, we find a file dev path source. Let's assert that these are in BCP47 format. We're going through directions, but let's assert that all of them match. Okay, now that we can make that assumption, we grab this followed by dev, and let's do the same for target. So we grab those two, and we want to lump them together into a directory. So let's make a something like this. We make it, and then we just copy. Exactly, and we copy the target into there. And then we can do the same thing for our dev test. Okay, so for that direction, we pick those two files and we put them into the directory. And we keep on doing that for all of these. Same thing for dev test. Exactly. So again, dev test. We move them into the dev test path, and that's it. At the end, we just delete. We go through the dev set. Not really. This will delete everything. OS list directories. Element path is what? Join. And then if is file, only then we'll remove it. Repeat the same thing for dev test. Exactly. And then after that, we just pull out those two to the root of, we pull out those two, we just move them to move the dev path to the dataset directory. Dataset directory is again just corpus name. Well, not exactly. Let's first rename. Let's now rename. Exactly. Let's rename this dev path to this, and let's rename the dev test as well. And now let's move to the dataset path. No, but I want to move them to the dataset directory. Okay, so this should be everything we want to do. Let's test this. Let's see whether this works as expected. This should be all we need. This should be exactly everything we need to do. Or we can just do like this. That's the new path. Exactly. And then new dev set path. Exactly. And then we move that guy here. Okay, looking good. Let's now test with a couple of directions. For example, we pick English, Latin to Russian Cyrillic and Turkish Latin script to use then is what? Which script? Latin. Those are some of the most resourceful languages. So let's just see whether this will do the job. Okay. Now let's kick off the run. Looking good. Okay, here we are. delete, oops, snap. Flores 202 dataset. What? Oh, there is no MD here, I guess. And repeat. Rerun. Okay. Delete, delete, delete. Create those. Go through them. Go through the directions. Create the source and the target. Create a directory. Here it is for English Latin. And then we copy and we copy. Exactly. So we have Russian Cyrillic and we have English. Looking good. Source dev test. This one, we do the same thing in dev test. And we copy. And we just repeat that a couple times for all of the directions that we care about. Okay, so you can see what we've done. We just extracted directions we care about. Now we go and we literally, if it's a file, delete it. And just do that until we are just left with our directions. And seeing here, hit F5, here we are. We are just left with our directions. And now we create new file names, we rename these. Dev should be called Flores dev. And this guy should be called Flores dev test. And then we move them all the way up to eval. And we move it up as well. And we're done. So here we now have everything we need. So the only thing that I forgot to do is to delete okay, a couple of things I messed up. I'm gonna fix that now. First things first is not the dataset directory, but directory. We move them up to here. And then we delete exactly. We remove the original dataset path. Actually, we remove the dataset directory. Because dataset path is what? Okay, yeah. Looking good. Let's repeat this. Let's delete everything under here. Just delete. And rerun. Rerun the whole thing. Okay. Rename. Move. Move. Until we are left with this. And then we move. We remove that one. Okay, that's it. So now we have Flores 202 dev with directions we care about. And we have Flores 202 dev test with directions we care about. That's it. That is ready now. Alternatively, we can leave them you can always re-download with all directions. Okay. Let's submit this. Download YAML files. Filter pi. Oh no, that's Stokes. We care about fair sec. Okay. What do we want to check in? We want to check in the non-YAML ones, so analyze data and download parallel corpora. Why is analyze data changed? Is it just the imports? Analyze data. Oh no, okay, language direction. Okay, that's just something that some fixes we made yesterday. Download. Hey Aleksa, big fan, good to catch you live. Admire your journey to DeepMind. Curious to know how was your daily routine, work timings at DeepMind. How is the work planned and structured at DeepMind, the project team? It's gonna be hard for me to now digress and tell you a bit more about that, but maybe if you can catch me in the server, I can tell you a bit more. But yeah, I don't have a TLDR for that. Just join the server here, by the way. Let me see, somebody joined it, Ashif Ali, West Bengal, India. He has interested in English to Bengali. Nice. So just in the pin list, you can find these documents. So here's the language champions doc. Let me just share it with him. And here are the tasks down below here. So we are looking for somebody who speaks Bengali actually. And we have a task down there, language champs tasks. Okay. Let's see what are the changes here. I modified download Flores. Anonymaze, again, sorry for not having a better answer, but again, I'm trying to focus on this stream on stuff that's roughly related to what we're doing. Eval datasets path, we've added this one. We just modified the make directories order here a bit, and then I uncommented Flores 202 because it's ready now. So that means we can add analyze data, and we can also add download corpora, commit that, prepare Flores 202 for eval, small fixes for analyze data script. Push that out. Oh, I forgot to pull the, okay. Snap. If I pull now, will it complain? No, it will not. Awesome. And then we can just do okay. Okay, that's we had a small push from Alex modifying the install script, so that's why it rejected my push. Okay, all good there. Let's see what are our next tasks. Let me go back to Notion. We are done with this. Now let's go and play with Apex. Let's see how Stopes is progressing. Okay, guys, look at this. So previously it took 2 hours to just to get to here, to get stuck on this patch. Now we are already at the very end. 256 to 279. This is like the penultimate batch, I think. Let me see how many do we have? 279. So we literally, this is like perfect outcome, because we missed out on what? 0 to 7. This is 0 indexed. This is 1 indexed. So this is actually 273. Okay, so this one kind of slowing down. Has slowing down these ones, but then we'll have these biggest ones in the last patch. Let's see whether we just, I suppose this one is running at the moment. Just a single process here. Okay, no, we're actually somewhere here. These two are running. This one is gonna finish now, and then we are left with this one. And then in the last patch we handled the last 6 of them, and we are ready. So this might take a couple more hours, but at least we don't have to wait. Yeah, no worries, man. Catch you on Discord. Join the Open NLLB project if you're curious about it. Let's go to the FairSec train script. FairSec. Let's find the train script. Actually, not this one, but instead train.py under FairSec CLI. This one. Okay. Let's kick off a run, and let's profile how quickly it goes to 1,000 steps. And then I think that number was somewhere about, let me think, we calculated roughly 16.6 hours for 100k steps. So that means, let me see, 16.6 hours for 100K steps. Let's convert that to minutes. So that many minutes for 100K, and then divided by 100, roughly 9.96, roughly 10 minutes for 1,000 steps. So 10 minutes for 1,000 steps. Let's see how faster we are with Apex. So let's go to the launch script. To the launch JSON, I mean config. Generate interactive, that's not it. Sweep by, that's not it. This one. So before, disable validation, that's fine. VenDB project, that's fine. So we had to remove this because we didn't have Apex and it was failing. Now we have Apex, so we can run this. So let's add this line and see how much faster are we. Okay, FP16 Atom stats. Is that the only thing? Only support with fused atom. Will we be hitting this? How can we know we're using Apex? Okay, making just a super quick break, and I'll be back in a couple of minutes, and then we're gonna see where and how Apex is used in FairSec and do the profiling. That won't take more than 10 minutes, ideally, because we're trying to obviously get faster than 10 minutes for 1,000 steps. Quick break, and I'll be back in a couple of minutes. Catch you soon, guys. Stretch your legs, just grab some air. I'm back. Let's go. Apex. Let's see where Apex is used. Let me just see where they call Apex. Okay. Okay, this is now just like textual files, actual data. Let's find all of the mentions of Apex in the repo. Okay. You may get better performance by installing NVIDIA's Apex library. From Apex, normalization, fuse atom. Will we be calling this? Okay. How does one pick something like this? Let's see. We probably won't be calling lamp optimizer, but let's see whether and how it is getting actually called. So there is this flag that I know if we pass it in without Apex, we had issues. So let's see which one of these we hit. Okay. Atom. And there is a CPU atom that we don't care about. Okay, I think we use atom, right? Do we mention atom here anywhere? Atom with atom FP16 atom stats. Okay. Let's go to train. Train script. Let us set this config and let's kick off the run. My stream might start, it will become a bit slower. Okay, we're hitting fuse atom because once we start training, almost all of my GPU capacity is used for training the MT system, and then the encoder for the video encoder is struggling because I'm using NVIDIA encoder. So there is some competition between rendering and sending the stream versus training. Hit the 5. Let's see, when do we start? Okay, here it is. Adam. Awesome, thanks SQ. Thanks for letting me know. Get fused Adam class. Okay, we return back the class. If you use fused Adam, if it's not none, if CUDA is available, if this class is not none, use old Adam. If that's false, okay, so using the fuse class, and then we call the fuse class with parameters with stat set to true and optimize config. Whoops. I got too deep into this. Okay, here we are. So we are inside of the fused Adam. That's cool. We set defaults. Nice. Nice. And then this is Fair-sec Adam, but with the optimized implementation. Okay. So let's see. Let's hit F. Again, we enter here, but we use optimized Adam, the fused Adam. So because of that, we are using fused Adam. Hit F5. And let's measure. Let's see roughly the time. I didn't. Well, actually, the training is going to be logging timestamps. So we'll be able to see. Okay, here we are when the B is starting. There's some error. Okay. Key error exponential average scale. What is this? And where did we fail? Process context. Let's see what this variable is. Add a factor, we don't care. CPU Adam. If we use this, then we set it to 1. This is a step. Good morning, Robert. Yes, there is some error in the fused Adam optimizer. Okay, let's see where exactly is that specified. Apparently nowhere. Okay, let's stop the run. Let's rerun the whole thing again. Curious how much faster it is gonna be with Apex compared to the baseline. Okay. Okay, here we are. Exponential average scale. Okay. Aha. So here it fails because this does not exist. Why? If length of the state is 0, only then do we... Let's go to the second sub-process. Why is this not specified? Let's see whether anybody complained already about this before we start losing our minds. Ah. Set to 1 there. If length of the state is 0. It should be initialized with this value. Is this some bug in the implementation or? let's just send them our solution to this. Let's just go here. Mismatch. Runtime error. Did we open up both of these using memory efficiency? Runtime during training. Okay. Let's see what they're hitting. Okay, I've apparently solved in some other version. Maybe, yeah, maybe let's see. We are using some old branch. Maybe. Are we using memory efficient FP16? Yes, we are. Okay, there is just a ton of references and activity, but nobody actually solved it. It's closed because what? Yeah, that's one of the issues with using old version of FairSec. Because NLLB branch was built for that version. Maybe we can, if we start hitting issues that are unsolvable, we can always migrate everything to the latest commit in FairSec. Huh. This is, by the way, super old, 2020. Let's see. Let's go to FairSec again. Fused atom inside of here. Let's find this in FairSec. Let's go to FairSec. Can we just put it here? Nice. What is this? Where is this stored? What's the path? Fairsec optimizers, under optimizers. Okay. Let's go here. Fused atom. And now let's search for the scale. This looks the same. Okay. So why is state never length of 0? State of P. Oh. Okay. This might have been a stupid bug, guys. Let me show you what. We have model check. It's probably pulling some data from model checkpoints. Let's see. Model checkpoints. Let's clear this. And let's rerun. That might have been everything we needed to do. So it was not hitting the state 0 because it was loading the checkpoints and then restarting from there. But in the meanwhile, we switched from regular atom to fused atom. And so that might have confused the code. Let's see whether that's the solution. Let's see. Fingers crossed. Yes. And now this will not fail. And we can hit F5. Just go and run freely. Go and run freely. We solved the fucking bug, guys. Nice. I can hear my GPU working. I can also see my stream is slower. You see it's lagging on your side, probably the video. The audio should be good because the audio is probably not using GPUs to transmit. Let's see, guys. Let's see what's going on. Okay. Epoch 1 update. Low scale. Let's let it run a bit. Feels good. Feels good to be this smart. I'm joking, of course. If I was smart, this error would have not happened in the first place. If I was truly smart. JSON, Flores. Pickle. Just looking at all of the files I have here. Duplicates. SPM. Model checkpoints. think this is the only path that we have that can cause some issues like that. Let me just double check here. Okay, we are progressing, guys. I see we are already at number of updates 300. Let's see how faster we are and if we are faster. Okay, data. We're just using the process data from before. And model checkpoints, that's one of the things that was causing us issues. Let's see whether anything else here is special. I don't see any other paths here. I don't see any other paths. I see the paths here, that's fine. Looking good, guys. Okay, let's wait for this. This is, by the way, almost the end of the stream. We usually stop around 3 p.m. CET. So let's just wait for this to finish. So far, so good. Let's see the timestamps here. The first one was at 49:35. We are now at 51:52. And almost halfway there. I think this might be like a 2x speed up, which is nice. Going from 16 hours to 8 hours matters when I'm burning through electricity bills on my side and having to wait for that long. So it looks like roughly 3 minutes to get halfway there. And then we can test without Apex. Let's see, 600 updates, a bit more to go, and 700 updates, let's go. Maybe not 2x exactly, but close. Some speed improvements. I'll have to rerun again with the original setup without that special flag, the FP16 atom stats. This one triggers the use of fused atom, as far as I understand. Or maybe, let me think. Or maybe just the fact that we installed Apex causes us to run fused atom by default. In that case, I might have to set a special flag, like use the old atom or something like that. I think I've seen that flag before. Okay, we are at 800 updates. Do you guys hear me? I know that the stream will be much slower because I'm running the training, but let me know if the sound is still alright. So we've done everything that was in the title of this video. Paper reading, we went through 2 papers. Profiling Apex, we're doing that right now. And Flores 202, we prepared Flores 202 just an hour ago or something. So that's cool. Okay, here we are almost at the end. So Epoch 1 update, number of updates 100. That one happened at this time step. Let's see when the 1001 happens. Or 1100, so that we have a difference of 1000. Let's wait for 1100. Guys, if you have any question, now is the right time, because I'm just waiting for this. Donations are also readily accepted. The last time we had a donation on the stream, that was cool. I didn't even know it's a possibility. Nick donated 5 euros and then 2 more. Okay, so this was a question we had in the chat as well. I'm gonna reply to it a bit later. By the way, guys, we have in a couple of days we'll have Niels Reimers from Cohere, director at Cohere, giving a talk about embeddings and will large language model skills search. So check it out. Join the talk on 6th of September, 4 p.m. CET. Here is the abstract of the talk as well. Okay, I think we're done. We can stop this run. Here we are. Let me stop this. Okay, 14:57:14. And then here we had 14:49:30. Let's say 40, that's 8 minutes. 7:40 and here 25. Exactly 8 minutes. I can stop the run. Let's stop the run. So that was 8 minutes, 400 steps. $4,000 steps. Why are these handles so weird? I don't know how to tag people sometimes. Okay, let's remove this. Let's put it here. Okay, and let's re-trigger the run, and let's see whether we run with the regular Adam, not the fused one. Go to train, hit run, and let's see whether we hit the fused Adam constructor or just the regular Adam. Okay. Let's try and hardcode none. That might be one solution, because it seems we are retrieving still the fused one. What does this atom FP16 stats what does it do? I'm not sure exactly what it does. So FP16 stats, what it does exactly. Let's see. Why are we not using fused atom V2? Let's understand the answers to those questions. So first, can we bump up the performance even higher by using V2? And the second question is, how do we force this to run without the fused atom now that we have it? So it seems it's only used in the actual construction. So use FP16 stats. Let's put that one. Let's go back here. So why do we need that? If you use FP16 stats, then FP16, otherwise FP32. Okay. Got it. This is just some... It's probably going to be even faster because we are using it. Okay. So let's see what this old atom was. Use old atom. Yes. Use old atom. That's how we're gonna force it, I think. Whoops, just stop. Use old atom. That's not how it's called though. It's called, we have to do it like this. Use old atom. Okay, let's go guys. Let's rerun and see what's the performance gain. Let's hit the init method and see whether we indeed skip the fused atom implementation. Okay. Let's go. Exactly. That's it. Hit F5, hit F5, run it. And we are off to the races. Let's see how fast we are with regular one, and then we can make a comparison. So 8 minutes for fused one. Let's see how fast can we get it to run now. Look at this pattern here. 5 multiplying by 2. Okay, something failed here. Minimum loss scale reached. Weird. Okay. How did we train this before? Why did I mess up? We can't set FP16 atom stats. We certainly never ran this. We certainly never ran this as well, because this was always false. So that means we were always running this. And then there is the optimizer config. Let's see what configs are there. Let's stop this. If it's failing, we can just ignore it and just assume that the Apex is better as we know it is. So let's go to train script. Let's kick off the run again. Let's see what the optimizer config. Learning rate, betas, epsilon, weight decay. We never ever touch those. Let's go. Maybe it was just some initial bad random seed or whatnot. Although the seed might be hard-coded already, so. Why? Oh. Okay. We're again being stupid. We have to clear. This is nasty. Just plain nasty. Delete this. Okay. Same bug, all good. Fairly sure this will not crash this time. We tried to reuse the fused atom checkpoint, and that was causing some issues. And I was like, oh, look at this interesting pattern. And that pattern was actually the bug. I was staring in the bug. Let's just make sure this is running. And if it's running, we are gonna stop the stream, because this will take roughly 10 minutes to complete for the run. And then I'll just report back after we resume the stream again, if that makes sense. Looking good. It looks like it's running. Let's just get the first log and then we are off to the races. Okay, here it is. Number of updates, 100. Guys, I'm ending the stream right now and then catch you again later in 30-40 minutes roughly is when I kick off the next stream. So let's say 3:50 p.m., which is in a bit less than 40 minutes. Catch you soon, guys. We're gonna continue. We're gonna see what's the result here. Let's also see where we stop with Stopes. If I open Stopes here, Stopes is still running. Probably the last batch or one of the last batches. Yeah, this is the last one. We're waiting for the slowest run to complete. And that should roughly be it. Catch you soon, guys. Cheers.